It's actually related to the polyprotics because what you're actually looking at is if you have a mixture of two acids, one of them is going to tend to control. So, for example, if you have a mixture of acids, one strong and one weak, then what happens is the strong acids are going to dissociate completely. That's a given. And the weak ones do not, which results in the pH is controlled by the strong. And here's the thing is that this is an equilibrium. So if you dump in a bunch here, you're automatically going to keep the weak acid from dissociating. Okay? So when we look at a problem, if we have 0.0525 molar nitric acid, it's going to be mixed with 0.15 molar. Calculate the pH of the solution. Well, if nitric acid is a strong, then we take the pH is going to be the negative log of the concentration, which is 0.025 molar. So you're going to end up with a pH of 1.6. And so what it's going to do is cause the HF to not dissociate. So on an aside, if you run the HF, and you don't have to on these at all, but I want you to see what happens. So I'm going to run this first one. HF is going to be H plus F minus, right? So initially we're going to have 0.15 molar here, but we're also going to initially have 0.025 here because remember the strong acid and the weak acid are in the same solution, so they're dumped. Okay, so we'll lose X here, gain X here, and gain X here because there's a 0. So at equilibrium, we'll have 15 minus X, 0.025 plus X, and X. So again, we need our Ka, which is 6.6 times 10 to the minus 4. So this is actually a relatively strong weak acid. So our Ka is going to be equal to H plus times F minus yields HF, which is equal to 0.025 plus X times X divided by 0.15 minus X is all equal to 6.6 times 10 to the minus 4th. Now, I'm going to make no assumptions, so I get x squared plus 0.02566x minus 9.9 times 10 to the minus 5th is equal to 0. So my x value will come out to be 0.0034. So if we look at our hydronium ion concentration, it's going to be the 0.025 plus 0.0034, which means it comes out to be a whopping 0.02841. So the pH is equal to 1.55. So if you look at the difference, you've dropped a whole 0.05 pH unit by letting it dissociate. Is that worth the work? No. So know that if you have mixtures of a strong and a weak, then the strong will control it. Now, what happens if you have two weaks? So the cyanide is 6.2 times 10 to the minus 10th, which means it's really weak. This is acetic acid, which has a Ka. These are both Kas of 1.8 times 10 to the minus 5. So notice you have 10 to the minus 5 to 10 to the minus 10. Which one do you think is going to control? The stronger will control. So in this case, that means that it's going to be C2H3O2 is going to dissociate into H plus C2H3O2 O2 minus. And we have an ICE table. We're going to have 0.15 here. 0, 0 minus X plus X plus X. 0.15 minus X, X, and X. This is strictly a Ka, which means that it's strictly the H plus times the conjugate H3O2 minus divided by the protonated. is equal to x squared divided by 0.15 minus x, which is all equal to 1.8 times 10 to the minus 5. So we end up with x squared plus 1.8 times 10 to the minus 5, x plus, minus 2.70 times 10 to the minus 6 is equal to 0. So x comes out equal to 0.001634, which is the H plus concentration, which means the pH comes out equal to 2.79. So if you're thinking about running the HCN, you could run it, but think about the previous problem. It didn't make much, and you had a strong. So this is a weak and a weak, and it's a much weaker acid. So basically, if you were to run it, the H plus concentration changes if you run it to 0.016, okay, versus 0.001634. So there's really no change in the pH. So remember, if you have a mixture, whichever species is stronger will control the pH of the solution. And so that's the only one you actually have to work.